Welcome to this explainer. Today we're unpacking the engineering puzzle behind how we actually measure voltage in a circuit. We're going to look at how we can take a highly sensitive, kind of delicate instrument and completely transform it into a robust tool. So let's just dive right in. But before we go building anything, we really have to ask ourselves, what exactly is happening inside the tool we use to measure volts? It's so easy to treat measurement tools as these mysterious black boxes. We just connect the leads, read the number on the screen, and move on. But to truly understand the physical world, we gotta look under the hood. The core mechanism inside isn't actually designed to measure massive voltages right out of the box. It's built around something highly sensitive. So the big question is, how do we bridge that gap? How do we take a super sensitive core component and make it work in the practical reality of a heavy-duty circuit? Well, let's start with a quick foundational definition. A voltmeter is simply an instrument used to measure the potential difference between 2 points in an electric circuit, directly in volts. That phrase, directly in volts, is actually absolutely crucial. It means the readout is already calibrated for immediate practical use. And hey, if we're dealing with a much smaller scale, say potential differences on the order of millivolts, we just call that a millivoltmeter. But the fundamental job is exactly the same. Tell us the difference in electrical potential from point A to point B. Okay, here is the core engineering challenge we're facing. To measure potential difference accurately, an ideal voltmeter practically needs infinite resistance. Why infinite? Well, because if it has low resistance, the current from the circuit is going to take a detour right through the voltmeter itself, which literally alters the exact voltage you're trying to measure. It's the classic observer effect in physics, right? The act of measuring changes the thing being measured. However, our base tool for this, the galvanometer, is super sensitive and inherently does not have that massive resistance. So it requires a serious modification to get anywhere close to that infinite ideal, just so it doesn't disrupt the circuit's natural flow. So, how do we actually pull off this modification? We start with our foundation, a pivoted type moving coil galvanometer. Think of this as a device that detects tiny amounts of electrical current by using a magnetic field to physically move a coil and a needle. Now, to stop this little device from drawing way too much current and totally messing up our circuit, we pull off a clever magic trick. We connect a really high resistance directly in series with that galvanometer. By doing this, the resultant resistance of our whole combined setup increases massively compared to the rest of the circuit. Now, it can safely sit right across those 2 points and measure the actual potential difference, without throwing a wrench into the system. Let's make this a bit more tangible. To actually construct this thing, we need to translate those physical coils and wires into specific mathematical variables, kind of like gathering the ingredients for a recipe. First up, we have G. That represents the natural inherent resistance of the galvanometer's coil itself. Next is Ig, which is a really important concept here. This is the exact specific amount of current required to make the galvanometer's needle swing all the way to its maximum limit, what we call full-scale deflection. Then we have V, which is our target. That's the maximum potential difference we actually want to be able to measure between our 2 points, A and B. And finally, R is the hero of our story today, the specific, calculated high resistance we're going to connect in series. All right, let's look at the math and see how all these ingredients actually come together. Now, don't let the letters intimidate you at all, because this formula is really just our old friend Ohm's law, wearing a slightly different hat. When we connect our new, modified device across those points A and B, the current flowing through our galvanometer, which remember we've capped at Ig for full-scale deflection, has to equal the total voltage V divided by the total resistance of our brand new setup. And because we wired our high resistor in series with the galvanometer coil, our total resistance is simply the resistance of the coil, G, plus the new resistance, R. So our base formula is just Ig equals V divided by the quantity, G plus R. Okay. Let's put our engineering hats on for a second. We already know G and Ig because, well, those are just the physical properties of the galvanometer we started with. And we know V because that's the specific voltage range we're trying to measure. So the absolutely only unknown here is R, the exact resistor we need to pull out of our toolkit. By using a little bit of basic algebra, we just rearrange the formula to solve this puzzle. We multiply both sides by the quantity G plus R and divide by Ig. This neatly isolates our total physical resistance on one side of the equation, giving us G plus R equals V divided by Ig. And to isolate R completely, we just subtract G from both sides. So we're left with R equals V divided by Ig minus G. Honestly, this isn't just a math equation, it's a literal blueprint. To find the precise high resistance R you need to solder into your device, you just take your target maximum voltage, divide it by the galvanometer's max current, and subtract the galvanometer's inherent coil resistance. If you plug in that specific resistor, boom, you win. And this perfectly sets up a fantastic conclusion from our source material. By doing this, the galvanometer will literally become a voltmeter of range 0 to V volts. It's such a satisfying aha moment. By connecting that exact mathematically derived resistance value in series, we've successfully converted this highly sensitive, delicate current detecting galvanometer into a robust, practical voltmeter. And the absolute best part? We engineered it to our exact specifications. If we wanted a completely different maximum voltage range tomorrow, we just recalculate R for the new V and swap out the resistor. It's really that elegant. Now, just to wrap up the math and double-check our work, let's look at the final internal resistance of our newly completed voltmeter. We'll call this RV. RV is simply the high resistance we added, R, plus the galvanometer's original resistance, G. Because we specifically chose R to be a very high value, RV ends up being incredibly high too. We've successfully simulated that infinite resistance ideal we talked about earlier. Our new voltmeter can now safely probe the circuit, giving us highly accurate readings without siphoning off the current and ruining the exact potential difference we're trying to observe. So we've solved the puzzle. We took a sensitive galvanometer, recognized that an ideal voltmeter actually needs near infinite resistance, and we achieved that by calculating and adding a precise, high-value resistor in series. But I want to leave you with this final kind of provocative thought to really test your understanding of circuit logic. We engineered infinite resistance to measure voltage without interrupting the circuit, right? Well, if you wanted to build an ammeter to measure the flow of current itself using this exact same galvanometer, how would you completely reverse this engineering logic? What kind of resistance would an ammeter realistically need, and how would you wire it? Think about that for a bit.